So let's say we want to pull some blocks along the ground. So we've got one block, call it M2. It's connected to another block, M1, along a frictiony ground. But then we've got this pulley over here where our motor's connected. To try and pull them. And that's got a string that's wrapped around, ties onto M1. And we'll say mass of the pulley is MP and radius is R. Friction on the ground is mu. If we're given mass of pulley, mass of block 1, mass of block 2, radius of the pulley, and friction on the ground, we need to find moment of inertia for the pulley, tension in the ropes. So we'll say this one's T1, T2. And acceleration of the blocks. We'll also be given torque. So this time we're controlling the motor at a certain torque, and we want to see how does that affect the blocks. So we'll put some numbers in here. We'll say static friction is 0.5, kinetic friction is 0.4. So we'll start out with the free body diagrams. Again, we'll have one free body diagram for each of the objects. So here on the pulley, we know that we've got mass of the pulley times gravity, normal force on the pulley. We've got a torque. And then we've got the tension pulling from the first block. Now for the block, we'll have gravitational torque, normal force on that block, friction force, and then the block is trying to move to the left because the tension is pulling it that way. So then the friction force is going to point to the right. And then it's also got the tension from the other block. So then the free body diagram for M2 looks almost exactly the same. It just doesn't have a second tension. So it'll be pulling here. Then we need a coordinate frame. So we'll say X goes along the ground and Y goes up. Then we can write the equations for each block, each direction. Because the first thing we'll have to check is if the blocks can actually slide. Is the motor pulling hard enough that the blocks will slide? And then if they do slide, we can figure out how fast. So a couple things that we can figure out beforehand: inertia. Yeah, basically just inertia. So I equals 1/2 MP R squared. So 1/2 times 3 times 0.2 squared equals 0.06 kilograms times meter squared. And then for each block, so we'll do each one in a different color. What matters on the pulley is the torque because it's not moving in X or Y, and there's no friction on the pulley. Friction's only on the blocks. So sum of the torques equals I alpha, which is going to be the applied torque minus the one from the tension, T1 times R. Okay, so this one has two unknowns, alpha and T1. So what we know, A equals R alpha. So alpha equals A over R. If we put this all in variable form, then we have 1/2 MP R squared times A over R. So then this R cancels with this R. We just have 1/2 MP R A, but still two unknowns, T1 and A. So now let's move on to the next block. So for block 1, we'll need to do sum of the forces in Y to get friction and normal. Well, first normal, then friction, and then sum of the forces in X. So sum of the forces in the Y equals 0. N equals M1G. And F equals mu times normal force. So F1 static is going to use a static coefficient, and F1 kinetic is going to equal kinetic coefficient. So if we put numbers in here, N1 equals 196 newtons. The static one is going to be 0.5 times 196, which equals 98. And the kinetic is 78. Now summing the forces in the X direction, that's going to equal M1A. Now note that both of the blocks have the same acceleration. Okay, they're both connected by the same rope. And that's the same A that we get the pulley's angular acceleration from. So there should only be one A. So M1A, that is positive. Let's see, we set it as positive going to the left. So M1A, that is going to be T1 minus T2 minus F1. Now here we have three unknowns, A, T1, and T2. So now finally moving on to the second one, block 2, sum of the forces in the Y equals 0. Normal force equals mg. And for this one, normal force is going to be 20 times 9.81. Oh shoot, I think I switched these. So now it'll be correct. So this is N2 equals 294 newtons. And then F equals mu times normal force. So static is going to be 147, just the 294 times the 0.5, and F2 kinetic equals 118. And then sum of the forces in the X direction equals M2 times acceleration. It's going to be T2 pulling to the left minus the friction force pulling to the right. So this one has two unknowns, A and T2, but total there's going to be 1, 2, 3 unknowns, T1, T2, A. And then we've got 1, 2, 3 equations. Torque, X force for 1, X force for 2. So the first thing we need to see is, do the blocks move at all? We got to do the static check. And for that, we need to see, is the torque from the motor big enough to overcome the torque from the blocks that's created by that tension in the rope? So we'll compare torque from the motor, compare that to the torque that is caused by these blocks, which is due to that friction. So static friction from 1 plus static friction from 2. Because this friction is what makes it hard to move the blocks. If there were no friction, then it would be easy. So comparing that, we see 100 was given in the problem for torque. And then we check, we add these static ones together, but so this is a torque, this is a force, so we multiply by the radius. So that's going to be 147 plus 98 times 0.2, which equals 49. 100 is greater than 49, so the motor is strong enough to pull the blocks. So now we've just got to solve these 3 different equations for the 3 different variables. Now looking at this, we can see that the red equation, we can relate acceleration and tension. The green equation, we can also relate an acceleration and tension. So if we can relate T2 to A and T1 to A, and then this blue equation has all 3, we can get everything in terms of A, solve out for A, and then go back and substitute to get tension. So that's what we're going to do. We rearrange this one, then we get T2 equals M2A plus F2. Then we rearrange this one, and we get T1 equals torque minus 1/2 MP R A. This is going to be divided by R. So now that we have expressions for T1 and T2, we can put them into this equation in the middle here. So we say sum of the forces in the X on block 1 equals M1A, which equals T1, which we can read from this equation above, torque divided by R minus 1/2 MPA. And then we have minus the second tension, so minus M2A minus F2. And then finally we have minus F1. So now if we get A, we need to get all the stuff with A on one side and everything else on the other side, because A is our only unknown here. So we've got A times M1 minus M2, or actually that's plus because it'll change when it moves to the other side, plus 1/2 MP equals torque divided by R minus F2 minus F1. So if we rearrange, A equals tau over R minus F2 minus F1 over M1 plus M2 plus 1/2 MP. So we put numbers into there. We've got 100 divided by 0.2 minus, and here we have to use kinetic because they're moving. So we'll go minus 118 minus 78 over 20 plus 30 plus 1.5. That comes out to be 5.9 meters per second squared, and that is to the left. So what we did here, we solved out one of the equations for T2 in terms of A, another equation for T1 in terms of A. Then we put them both into the third equation, solved out for A. So now we can go back, plug A in, and solve for each of these others. So T2 equal, that's going to be 30 times 5.9, which is 236. And then T1, it's going to be 100 divided by 0.2 minus mass of the pulley, which is 3 times 5.9 over 2. T1 equals 491 newtons. Now just for reality check, it shows T1 is greater than T2. And that is reasonable because T1 has to hold on to both of the blocks. It's dragging both of them, whereas T2 is only dragging the second block. Okay, so the procedure for all of these kinetics problems is same as before. First thing, we draw free body diagrams, one for each object. Second, we assign the coordinate frame. Third, we write the equations. And by looking at the free body diagrams, you'll kind of know what equations to write for each one. It could be Y force, X force, torque, or some combination. And finally, you solve those equations to figure out what the unknowns are.